Heading, all of you write down. So this portion of this chapter is, easier than the previous one. We don't have, conditions like we did in thermodynamics. But yes, importance of this chapter, of this portion, if you see, it is equally important. Whether you're gonna write, NEET or JE, this portion is very important. We don't have, this part is not that big. Okay, we can finish this early. But the thing is, they definitely ask question from this. So obviously, if you see the importance and advantage of this portion, if you are very good at it, then it's very huge because there's a number of things you need to study over here. And then definitely, since questions you get from this point also, so you can solve those questions. Sometimes what happens, they won't even touch thermodynamics part. They'll ask question from this only, thermochemistry. Okay, so don't consider this as not that important. Okay, it is easier to score marks in this particular portion. Achha. Okay, so this is okay. Okay, so write down in this chapter or in this part, we will be studying the energy change in a chemical system, the energy change between a chemical system and surroundings. When let it be like this only. Produce surroundings. We can have any kind of chemical reaction. We can have a phase, or we can have any normal chemical reaction. So whatever kind of reaction is there, how the energy change is taking place between system and surroundings, that we are going to study. Right? It is also named as, this chapter is also named as chemical energetics. Chemical energetics. And this is based on float. That is first law of thermodynamics. Okay, energy is conserved. So there are only two possibilities in a chemical reaction. Like either the energy will get absorbed or the energy will get released, mostly. However, delta H zero is also possible, but very rare. Okay, mostly we have two conditions where the energy is getting evolved, where the energy is getting absorbed, right, consumes. Okay, so whenever we have energy evolve or energy consumes, we can represent in a chemical reaction. Right? For example, you see, if I write down one reaction here, we have 2 SO2 gas plus O2 gas. It gives 2 SO3 gas, and we'll write plus 694 kilojoule of energy. So what do you mean by this? Right? Here, the energy that we have, an energy of this. The difference in energy of this minus this is minus of 694 kilojoule. Whenever you write plus sign over here, right, it means the heat is evolved or absorbed. Tell me. Heat is evolved or absorbed? Evolved, right? So this plus sign means that delta H is negative. If you write down delta H for this reaction, that would be minus 694 kilojoule. Okay. If you write negative sign here, then delta H would be positive, energy is getting consumed. Like for example, you see, we have a reaction N2 gas plus O2 gas plus O2 gas. It gives 2NO, 2NO minus 180 kilojoule of energy. Roughly, I'm writing it down. So delta H would be what? Delta H is positive here. Okay, endothermic reaction. Okay, so obviously we have heat involved in this reactant product. So what would be the heat of a reaction? Copy this down first. Then heading right down. No, it's not nice. The contrast is too high. I knew that you will text this. Oro. The contrast is too high. You'll get a strain in your eyes. Yeah. Okay. So write down heat of reaction. We also call it as enthalpy of reaction. So basically here we are going to study about the different types of enthalpy of reactions. Like we can have enthalpy of combustion, enthalpy of formation, enthalpy of neutralization, enthalpy of solution, many things we have. Okay. So basically these are the definitions, right? We have few key points that you need to keep in mind, but it is basically definitions, and based on that you have to do some addition or subtraction in order to get the desired result as per the question. How do we do that? We'll discuss all those things. So write down first of all heat of reaction. It is defined as the amount of heat. It is the amount of heat evolved or absorbed, evolved or absorbed, both, right? Amount of heat evolve or absorb when quantities of substance, or write down like this, when the given substance reacts completely, or we can say when the reaction is over, reacts completely, or when the reaction is over. The enthalpy of reaction is equals to the summation of enthalpy of product minus summation of enthalpy of reactant. We'll write down the sum of the energy of product minus sum of the energy of reactant. That is the enthalpy of reactant. Product minus reactant, basically. Okay. Next, write down factors affecting. This is not that important. Just you need to have this information that what are factors which affects the heat of the reaction. Write down factors affecting delta H R. It's enthalpy change. R stands for reaction. First one is the physical state. Physical state of reactant and product. Physical state of reactant and product. With one example, just you need to know, like, they may ask you this particular comparison, but values you don't have to memorize. How it affects, that is not important. But if you look at this, example, you will understand. Like suppose I'm taking H2 gas and half of O2 gas. It forms H2O, gas, and the enthalpy change in this reaction is, all these are experimental. This is the value which is given, right? You cannot find out this if certain things are not given in the question, right? So this is given, delta H is this. Similarly, if it is gas, then this. And if you have H2 gas and half of O2 gas equals to H2O liquid, the enthalpy change would be, if it is liquid, then it is find out to be 68.32 kilocalorie. So you can see obviously there's a difference in enthalpy change. That's why we say that the physical state of reactant or product affects the enthalpy of the reaction. Copy this down. Okay. Now the second factor we have, second factor is the allotropic forms of element. the allotropic forms. Same thing here, you see. Carbon, if you are taking different allotropes, suppose for carbon, one of the allotrope we are taking diamond plus O2 gas. This converts into CO2 gas plus, if you look at the enthalpy change here, delta H is found to be minus 94.3 kilocalorie. And if the carbon, if you take graphite with O2 gas, it forms CO2 gas. So delta H for this reaction is minus 97.6 kilocalorie. So you see different value we are getting. So allotropic form is also a factor we have here. Apart from this two, we can have another factors like temperature. Not always, but temperature also you can consider. We can also have, quantities of reactant. Is a factor here. We can also have the condition, okay? The condition of reactant and the reaction actually. Condition at which the reaction is taking place. Okay, see, temperature is not always a factor. It is a factor when the heat capacity is a function of temperature. If it is not, then temperature is not a factor. If heat capacity is a function of temperature. So all these 5 factors we have which affects the heat of the reaction. Copied? One second, guys. Okay. Yes. Now, Yes. You see next we have different types of enthalpy. Write down the types of enthalpies of reaction. Acha, one second, just a 1 second. We have one more thing here. That is thermochemical equation. Heading right down, thermochemical equation. Not at all important, but I'll tell you what is thermochemical equation. Just you need to know the term here, right? Thermochemical equation is which one? Acha, that one. Okay, once again. See, basically, example of temperature is not a factor. See, usually what happens, if you look at the actual scenario here, just a second, Ansh, once again. If you look at the actual scenario here, right, then specific heat capacity depends upon temperature for every reaction. There will be some change in specific capacity when you change the temperature. But in the for solving questions, we don't consider the variations in a specific capacity with respect to temperature if it is not mentioned in the question. Are you getting my point? Yeah, right. So if it is not mentioned in the question, then we ignore this, relation of specific heat capacity and temperature. Most of the time, the relation would not be given. Like suppose if I give you one example, suppose delta H you need to find out, which is NCPDT, correct? And if CP relation is given with respect to temperature, like suppose we have, 2T square plus 3T plus 10. This kind of some quadratic equation or some relation of specific heat capacity with temperature is given. Then what you need to do? The CP you need to substitute over here when you differentiate this to find out the exact value. So we'll assume this if it is given in the question. Otherwise, we'll take it as constant. Clear? Yeah. Ansh, your doubt is harder to see. It's not like that. Uh, Graphite is more stable, right? The graphite form is more stable than diamond. That's why the natural, form of carbon in which it exists in nature is graphite only. It's not diamond. However, at very high pressure, we can convert carbon into diamond. That's possible, extremely high pressure. But the natural existing form of carbon is graphite because it is more stable in graphite form. And because of its high stability only, we have that difference in enthalpy. That's why we say every allotropic form has its own stability, has its own energy, right? That's why if the allotropic form will change in the reaction, the enthalpy of the reaction will also get changed. Got it? Thermochemical equation you write down. Write down. These are the equation which represents thermal as well as chemical change. Like whatever reactions we have written so far in this particular chapter, that is thermochemical equation. Suppose I have this reaction A gas, the state must be mentioned, solid, liquid, gas, right? B liquid suppose gives C solid. Randomly I have written some equation here. So state of each reactant or product must be mentioned, plus whatever the enthalpy change is there, plus X kilojoule. So for example, I'm assuming this enthalpy change must also be mentioned. So when the chemical change as well as thermal change is there mentioned in the equation, it is said to be thermochemical equations. Clear, no doubt? Okay. Next, you see the heading, write down different types of enthalpies of reaction. Types of enthalpies. Okay. The first type you write down, it is enthalpy of formation. Enthalpy of formation. It is represented by delta FH. If it is a standard state, then this would be not over here. Standard state. Enthalpy of formation. Definition, write down. Let me just put this in the charge, my laptop, 1 second. Okay, write down the definition here. It is the enthalpy change. It is the enthalpy change when 1 mole of a compound when 1 mole of a compound is formed from its constituent element. Constituent element which should be in their reference state or standard state. Right? So two things are important here. One is forms from its constituent element. This is important. Another one is 1 mole should be formed, constituent element, and reference state. These three things are important here. What do you mean by constituent element? Suppose carbon dioxide is forming. So what are the constituent elements of carbon dioxide? It is carbon and oxygen. This is the constituent element of carbon dioxide. So these constituent elements must be there in their reference state, the state in which it naturally exists. Like for carbon, the natural state, the reference state is graphite, it is not diamond. So it must be in graphite. Oxygen, O2, it is the gas, the natural state we have. Right? So natural state must be there, plus only 1 mole of substance must be formed. If 1 mole is not there, then the enthalpy that we get in this reaction, that enthalpy is not enthalpy of formation. See, enthalpy is what? Enthalpy is an extensive property, right? Enthalpy is an extensive, yes or no? Is extensive. So when we define an extensive property, whether it is enthalpy or any other property, we always define the amount that we are taking. It is an extensive property. So to define an extensive property, we always define the amount, because 1 mole you take, you will have a definite value of energy. 100 mole you take, the value will be more, right? So what is the amount you're taking in order to define the enthalpy of formation? The amount is what? Amount is 1 mole. Did you get it? Right. We'll finish this enthalpy of formation and then we'll have a break. 1 second. Let me finish this. Okay. So you see, two questions we'll discuss on this. The first one is, which of these reaction represents which of these reactions represents the delta FH of CO2. Delta FH means enthalpy of formation. I'm going back 1 second. Enthalpy of formation of CO2. Done? Yeah. So 4 reactions I'm writing down here. So first one is CH4 gas plus 2O2 gas gives CO2 gas and H2O liquid. First one is this. The second one, we have CaCO3 solid gives CaO solid plus CO2 gas. Third one is carbon graphite plus O2 gas gives CO2 gas. Carbon, we have diamond plus O2 gas gives CO2 gas. Which one represents the enthalpy of formation of carbon dioxide? Clear? What is the answer? Tell me. Yeah, obviously the first two you can eliminate easily because these are not the constituent elements, these are compounds over here. Carbon and graphite, we know diamond is not the reference state of carbon, it is the third one. Okay, now based on this, you see one question they asked in JE. What is that question? I'll tell you. The question is, which of these reactions represents the enthalpy of formation? After this, we'll take a break. Which of this reaction, these reactions represents the enthalpy of formation? The first one is half of H2 gas plus half of Br2 gas gives HBr gas. The second one is N2 gas plus 3H2 gas gives 2NH3 gas. Third one is half of H2 gas plus half of I2 gas gives HI gas. And the last one is half of H2 gas plus half of Cl2 gas gives HCl gas. Okay, now you see this. The answer for this question is option D. This is wrong, this is wrong, and this is wrong. Why this is wrong? Because the reference state for bromine, you should know, it is liquid. It is not gas. And you should know this. You should know this information. The same question was asked in JE, exact. The reference state is liquid, not possible. This, the reference state is fine, but here it is given 2 moles. It should be what? It should be 1 mole. Hence, this is also not right. H2I2, I2, the reference state is solid. It is not gas. This is also not correct. Chlorine, the reference state is gas, and this one is fine. So you should know the reference state of the element. Correct? Got it? So 1 second, I'll go back. This one. Yes, tell me. Ansh, done. 1 second, Auto. Okay. So you should know these things, right? What is the reference? I'll give you some example here, just you can keep in mind. One note you write down after this. Done, Oro? Huh. One note you write down. The enthalpy of formation delta FH, the enthalpy of formation of substance in pure or standard state, or a standard state is 0. Okay, pure or standard state is 0. So for those, like for molecules for which delta F of H, like enthalpy formation is 0, is we have O2 gaseous state, enthalpy of formation is 0. We have H2 gaseous state, enthalpy of formation is 0. N2 gaseous state, enthalpy of formation is 0. Carbon graphite form, the enthalpy formation is 0. Sometimes they also write down solid. Solid, you understand graphite only, if diamond is not mentioned. Reference rate is 0. Phosphorus, if you have white phosphorus, delta FH is 0. Sulfur, if it is rhombic sulfur, delta FH is 0. Tin, if you have white tin, delta FH is 0. Correct? Copy this down. So for all these elements, the standard state, you know, there the enthalpy of formation would be 0. Okay. Now, one last thing you see, if you have a reaction, A, their state is given, A gas, I'm assuming, B gas, I'm assuming, gives C gas and D gas. Suppose we have this reaction. So enthalpy of formation of C and D would be delta FH, obviously for 1 mole, is equals to the enthalpy of formation of C plus enthalpy of formation of D minus the reactant one, enthalpy of formation of A plus enthalpy of formation of B. This is the enthalpy of formation, product minus reactant, this you need to do. And it should be 1 mole. If it is not 1 mole, then this won't be the enthalpy of formation. Keep that in mind. Okay. Fine. Take a break now. After the break, we'll resume with this. Some other enthalpy term we'll see. 6:35 will resume. Take a break.